So the EVM is considered to be a very simple virtual machine, but it does have a lot of nuances. The devil is often in the details. So in this talk, I want to explain some of this deviations or interesting aspects of EVM that will also affect how you write Solidity and how Solidity is itself designed. So to set the mood, let's start with a trivia question. How many of you know what a precompile is? Raise your hand. Okay. If you don't know what a precompile is, it is simply like a system contract where they are contracts that are pre-deployed on the chain, and they can do some operations. As an example, there is a precompile called EC-recover that is deployed at the address 1, and you can do elliptic curve operations. You can do elliptic curve cryptography operations using this precompile. Another example is the identity precompile. It's deployed at address 4. It returns whatever data that it gets sent in the call data. So my question is, what is the Xcode size of the identity precompile? So if you don't know what Xcode size is, it's simply returning the amount of code in bytes of the address. So what do you think is the Xcode size of the identity? Any guesses? No guesses? It sounds strange, but it executes some code, right? Let's see what it is later. As a follow-up, let's think about the same question, but in the context of Solidity. So we have an interface here called magic return check. So oftentimes there are many EIPs that require you to return a magic selector, often like a 4-byte data, when the operation was successful. So we have an interface here called magic return check, and it must return the function signature, the selector, as a return data if it succeeds. So now let's look at the magic check, but we're going to do the magic check on the address 4, the identity precompile. So what do you think will happen here? Will the call to magic check succeed? Will it revert? Any guesses? Any guesses? Would it reward? Would it succeed? Just pick one among the two. Sorry, what? It failed. Why? We'll talk about it later as well. So let's talk with the first interesting aspect of EVM. It's going to be the instruction called return data copy. So this was introduced back in 2017 in the Byzantium hard fork. And it's a very important instruction in the sense that it allows you to fully implement dynamic types in the ABI. So to explain this in more detail, let's see an interface. We call this interface to be nameable, and it just has a function called name. It returns a string in memory. So suppose we call this function in a Solidity contract using nameable of whatever address.name. You really need to have this return data copy instruction to copy a dynamic amount of data from the return data buffer into memory. Why does it have to be return data copy? Because we don't know the length of the string that's going to come back to us. Could be from 32 bytes to 64 byte. If we actually knew it, we don't really need return data copy anymore. So as a more practical use case, there is an idea called a minimal proxy contract. So the idea is that you want to create this proxy which just delegate calls whatever data that comes to the proxy to an implementation contract. And depending on whether the implementation contract call succeeded or not, you would either revert or return with whatever data came back. So you really need to have return data copy that just copies everything in the return data and then return back whatever came in the return data as a reward or a return. So here's like a very two-line pseudocode of how it works. As a practical example, this is used in many smart contract wallets where there is one implementation contract that can be pretty big and you want to have like cheap copies of it. It's typically called clones. So the clones can be very cheap to deploy and still have the same functionality. So there is one nuance in return data copy that we will look into right now. So what happens in general in EVM when there is out-of-bounds access? Let's look into memory load. So if you want to read from a location in memory, what you do is use the instruction mload. So if the offset is somewhere that it is never used, in EVM terms, we call it if the offset is above what is the current value of the maximum size of the memory, this would just return 0. Similarly, in call data copy, if you're going to read from some location in the call data that's above the call data size, this would just treat, the instruction would treat it as if it's an empty buffer, or you just assume that the values are going to be 0. There are many other cases in the EVM where whenever there is an out-of-bounds access, it's treated as a reading from 0. But not in the case of return data copy. Out-of-bound access in return data copy rewards, unlike every other out-of-bounds access in call data copy, mload, or call data load. How did this happen? So the original proposal actually suggested the same semantics as call data copy, where if there is an out-of-bounds access, then you treat it as reading 0. But what happened in the end was there was a comment in the GitHub pull request proposing the EIP, and the commenter made a point that you never should access return data outside of the bounds. So why don't we just reward instead of just reading it as 0? So the EIP was updated to the new semantics, which is reward on out-of-bounds read. And this is a very small deviation, and I'll tell you how this affects some other applications later in the line, especially even a bug in the Solidity compiler. So here is like a different example, which is what happens if you don't use return data copy. And this is what I would consider as a small bug in the Viper's clone method. So as I mentioned before, there are these like minimal proxy contracts which just forwards everything over to like an implementation, and then you just return everything back. So the Viper's clone method before the version 0.29, what they did was they never used return data copy. So as I mentioned, if there is dynamic data, you have to use return data copy. So instead of that, they just went for a hard-coded offset. They just hard-coded that you will just copy everything up to Surex 1,000 bytes. So the problem is that you always get like Surex 1,000 bytes of data, regardless of how much data came out of the implementation contract. Even if there was 32 bytes, you get Surex 1,000 bytes. The question you might ask is, can we actually do that? It turns out that in the ABI standard, it allows you to add extra data. So as an example here, so we have some Solidity code, u in x equal to, it calls some interface and it calls some function, but you only expect a u int x. So the ABI only really expects 32 bytes to come back, but if you just add more data, it's fine. The Solidity decoder would actually decode it correctly, just like many other like applications. There are some like smart contract implementation that actually like really uses this. One typical example is what's called clones with immutables. They are a proxy contract, but they just add a little more data to the call data, and they just like forward it over to the implementation. But there are many applications which like to be more restrictive. They want to exactly fix how much call data is you're gonna. How much return data you are getting. One example is what's called safe ERC libraries. So to give some context here, the ERC20 implementation has some real-world flaws in the sense that there are some like popular tokens that aren't implemented properly. So what people do if they want to interface with every ERC20 token is they try to be a little more accepting to the standard. So as an example, the Open Zeppelin's Safe ERC20 contract, it allows you to work with a wider set of ERC20 contract that doesn't fully follow the standard. So there are some implementation that that restricts that, okay, if you are using an ERC20 contract and if it expects just 32 bytes of data, if you return more than 32 bytes, you just revert. It doesn't accept it. So if you use the all wiper clone implementation, and if you had stricter ABI checks, then the use of this proxy, which doesn't use return data copy, it would fail. So this is an example of like an implementation that's bad for interoperability. This was since fixed in 0.29, but I just wanted to make this as an example of why you really need dynamic data. So after this, we will move on to what happened. I mean, the decision to make this exception in the EVM, it really bit us back in a feature, and I'm going to explain you what happened here. So there is an optimizer step in the Solidity optimizer that would remove memory copies if the copied region is never read from again. So from a practical point of view, if you're going to copy to memory but you never what it or read it later, you might as well just remove it. So in case of return data copy, what this means is that you're going to copy from a memory pointer. You're going to copy from a return data pointer of length, and we're going to copy it to memory pointer and to the region that ends with memory pointer plus length. And if we know that this region is never read after this, we could just remove this instruction. But here is where the reverting semantics can be tricky. So this can only be removed if there is no out-of-bounds read in the return data access. And turns out that one of the implementation in Solidity actually did not care about this this out-of-bounds case. So there would be a deviation in the semantics where the unoptimized code can revert, but the optimized code will not revert because we just removed something that would have reverted. It was very interesting to find this bug because this idea kind of came out when we were triaging a false positive that was produced by Solidity's fuzzer. So Solidity has a fuzzer which will try to generate random Solidity code, and it would run it against two different code generator. And if there is a deviation in the semantics, we can see, oh, there is a Solidity program that should probably behave in a different way. Maybe there is a compiler bug. So there was a Solidity contract that the first was generated that showed some deviation, but it was not exactly this. But while looking into it, we actually saw that okay, we were not actually including this reverting semantics into the optimizer step. But this ended up having very low impact because almost every use of return data copy is just copying everything from the return data buffer into the memory. So the problem of this the problem of this bug would only occur if the offsets are static, which was very rare in actual code. So it was a very low impact bug, but still a very interesting bug that had something to do with the underlying design decisions made for the EVM. Now let's look into a different problem in the EVM. So here is a small snippet of Solidity. It's a low-level call that just calls a contract with some data, and it would just have the success value, which is a Boolean, and whatever was returned from the contract as a return type. So what happens? What happens to this call when the address doesn't have any code? Any guesses? Go on. Sorry? No, it's a low-level call.
So there's no coded address, and you're calling a call. Oh, it's a dot call. Okay, never mind.
Yeah.
You're not casting.
Yeah.
If you cast it to something and just call it, it will revert. This gets us a silent success.
Yeah, exactly. It is a silent success, as you said. So the value of S here would be true. So low-level calls to accounts without code will succeed in the EVM. And this can be sometimes problematic if you want to actually call a contract and all of a sudden there is no contract, but it still succeeds. So what Solidity does is it inserts something called like it inserts something called an Xcode size check. So before every high-level call in Solidity, what we do is we add the small expression that checks if the Xcode size of that address is at least 1. And if it is not 1, then it would just revert early on. But the problem here is that this is a little bit expensive. It actually costs 100 gas to do this check, and this was after the IP 2929 introduced in the Berlin hard fork. And it used to be even more in the past. It used to be 700 gas. So people were very, very upset about this check when they knew that there was going to be code. But we couldn't really remove it because it introduced some foot gun in Solidity. But can we actually optimize this even better? So we can make one observation here. The observation is that accounts without code cannot return data, right? And if you're going to and this means that if this is an address without code, then it's actually going to the value of return is going to be just empty. So if we expect that this return data is going to be used somehow, and if you expect that if we expect that the return data is empty and it's going to be used later and it reverts, then we can skip the Xcode size check. So the observation here is that if the return data is going to be used, and if the empty case would revert anyway, so we might as well just skip this check. We can save 100 gas by doing that. So in case of high-level Solidity, what happens is if there is a call like this, a uint A is assigned to a call to the interface and a function. If we call a code that cannot return data, if you try to do the decoding for the uint A, the API decoding will fail and there will be a high-level reward. So in this case, regardless of whether there's an Xcode size check, it's bound to reward anyway. So we might as well just remove the Xcode size greater than or equal to 0. As long as this condition is true, F has to return at least something. If F does not return anything, we can't do this. So this leads to a very interesting and counterintuitive idea that if you have a function that actually returns something, it actually is cheaper because we can skip this Xcode size check. But this only happened after Solidity 0810, so that's the one caveat here. And there are many EIP standards that actually use this as a magic value. So what they do is they say that a certain function should actually reward a magic byte, and only then you can really consider the application to be truly correct. Here is an example of of this in actual use. So there is an interface ERC1271. It's sort of an extension of EIP 712, which defines how you can encode and sign some data, and you want to figure out a way to allow smart contracts to actually sign data. So it has this following statement, which says it must return the magic value 0x, 1, 2, etc. when the function passes. And this magic value is nothing but the function signature of this function, the 4-byte selector. Now let's go back to the rule that we used to make the optimization. The rule was accounts without code cannot really return data. Is that actually true? What do you think? Can you have an address which is empty, but it can actually return data? I almost gave a hint. The precompiles can actually return data, but the Xcode size of the precompile is actually 0. So this optimization is a little bit weird when you use precompiles along with it, but we think people use precompiles rather rarely, and especially not in a high-level code. So we think this optimization is sort of worth it, even though it's practically a breaking change. So let's go back to the Solidity trivia. So we have the identity precompile, and we're going to encode this function call. And what happens if you call identity precompile with this function? So it turns out that before 0810, this function would actually revert, but after 0810, it would actually succeed. Can anyone tell me why it would revert before 0810? It's because of the Xcode size check. This is a high-level code. This is a high-level call, so we have to check if there is some code on the account. And when you do an Xcode size check on the precompile, there is no code, and you would just revert. But turns out that after 0810, the Xcode size check is skipped, and if you call the identity precompile, the first 4 bytes are going to be the selector of foo, followed by the 32-byte encoded value of this uint. So it's going to return everything back. And as I mentioned before, in Solidity, it doesn't. We don't care if you return more data than needed, as long as you return at least 32 bytes, which is needed for this 4-byte, and you just truncate. You just truncate it, and then it turns out that the selector is indeed whatever was provided. So what can we really learn from everything I mentioned before? About the return data copy, we learned that initially the proposal was just have it same as every other instruction. But we wanted to introduce this small micro optimization where it's very rare to actually have an out of bounds access. So we might as well just revert. But we saw what happened when you introduce this deviation and micro optimization. Some other tool down the line will not account for this, and there will be a bug somewhere. So something we can learn from the return data copy is that we should start looking into the big picture versus one small change when we are proposing new changes. And the second thing I can tell from the talk is a lot of rules in the EVM has exceptions. I mentioned the return data copy exception, the exception about precompiles and Xcode size. We should always keep it in mind when you're trying to design something. There's always something that will come along, and there is always some exception that will come along and might bite you back. And one thing I can tell you when you are trying to design is try to avoid complexity if you can do it. sometimes a small micro optimization might actually not be worth it if you're designing something that's going to be used by millions of people. Not everyone might know this small edge case that you just introduced to your design. Thank you.